Our topic: extraction, verification, and usage of short-haul Opto VCSEL model, sponsored by Keysight Technologies, formerly Agilent Electronics Measurement Group. Effective June 1st, Keysight will resume responsibility for selling and supporting high-performance products to all customers in the U.S. and Canada through its direct sales force. I'm Bill Wong, Technology Editor for Electronic Design. Let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. To maximize the slide presentation window, press the small green button at the top right corner of the slide window. We welcome your question during today's event. Just type your question into the question window on the side of the screen and hit the submit button. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send your questions in at any time. Please also be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a copy of the slides by clicking a green folder icon in the toolbar beneath the slides. Now, let me introduce today's speaker. Graham Riley received his BS in Communication Engineering from Plymouth University and an MS in Microwaves and Modern Optics from the University College London. He's an application engineer for Keysight, ease of EDA, with more than 25 years experience in the use and application of analog, RF, and microwave EDA software. Now, let me turn things over to our presenter. Graham, the floor is yours.
Thank you, Bill. So welcome, everyone. And thank you for attending this webcast in the Tutorials in Signal Integrity series. And the topic for today's webcast, as Bill said, is extraction, verification, and usage of a short-haul Opto VCSEL model. And in this presentation, we'll be looking at the challenges of modeling and simulation for the critical VCSEL element in an optical link in the context of short-range data center type communications. So let's look at the agenda. You'll see here I'm going to do an introduction which will just give you some context for the rest of the talk. Because we're talking about modeling, we're also going to talk about simulation, and we're going to talk about simulation options for optical links, looking specifically at channel simulation and IBIS-AMI modeling. And then we're going to look at the place of the VCSEL, the vertical cavity surface emitting laser, to give it its full name, in that picture. And then we'll go on and we'll do the detailed work on the VCSEL itself, choosing a model, what's in the model, what kind of model we have chosen, how to extract it, and then how we verify that it's working. And I'll finish up by showing you some examples of an optical link simulation running inside of a channel simulator. So before we go on and do the detailed stuff, let's look at some background information. So I think everyone's aware that the internet and the data that's flowing on it is growing at an incredible rate. This detail slide here comes from 2013, but I think we're pretty much on forecast for what I know to enter what's called the zettabyte era. That's an awfully big number. It's a bit, well, you can't even get your mind around such a large number, but it's certainly something that we're all having to deal with because of the pressure that's putting on the internet and the infrastructure. So this is really where the growth is coming from, and that's you and me. Where we're driving an increased usage in traffic with increasing HD video, a lot of it, audio, and many other things. So the traffic is increasing. Now the question then becomes, where is all this data being sourced? Where is all this happening? We call it the cloud. But really, it's a data center. There are many data centers around the country and around the world. And each of these data centers is having to handle this increasing traffic, this capacity, this need for speed and capacity that is being driven by you and me. If you look at the graphic on the left side, you'll see the ever-increasing speed demands of the core networking. That's the red line, and the actual server I/O. Even there, the data rates are getting extremely fast. The graphic shows 100 gigabit Ethernet. That's kind of current standard now, and people are now looking towards 400 gigabit Ethernet in the future. So what does this mean for you and me as designers in this environment? Well, here's one way of looking at the problem, and that is saying, well, if we're going to achieve all this speed, how are we going to do it? And you can see on this slide there's a number of, if you like, design variables that we have to work with. There's certainly going to higher order modulation. Clearly just pushing on the signaling rate. That's another way of doing it. And then multiplexing, whether that's spatial or wavelengths. All of these things are out there and in play. The graphic shows green is established technology. Again, this is a couple years old. The yellow is where people were working a couple years back. Some of this stuff is now getting close to being in systems. And then there's the very hairy stuff, the place where we all get nervous, and that's where the red lines are, and that's where the risk is. To take a slightly different cut at this and say, well, what are we looking at here in the problem? Well, if you look at the phi in an Ethernet stack, you can see that phi actually consists of a couple of important areas. One is electrical functions, things like error correction and coding. And then because there's an optical part of the phi, then clearly there's an set of optical issues that need to be dealt with, and that's where our VCSEL fits in as a critical part of that optical phi. But you can see that the phi itself is electrical and optical. So we have a lot of challenges. We have the need to work with electrical and optical. So one way of reducing the risk for all of this is to do simulation, of course, and I know that's something that so many people are out there doing right now with different kinds of tools. So I'm going to briefly look here on the next section at simulation options. As I said, we'll focus then on a couple of particular things related to channel simulation, and then we'll move on to the VCSEL. So if you're going to be doing simulation, what are you really looking for here? You're looking to measure how good is the phi, against a specification of some kind. So you clearly need to provide an accurate set of models and simulators that can work with those models. But beyond that, you also need to be able to deal with the complete design, not just the individual parts, but look at the phi as a whole, and then be able to validate your simulation against measured data. So those are some general challenges of working in the phi arena. In the case of electro optical, we need to be able to deal with both the electrical and the optical in one simulation if we can. So let's look then at the optical transceiver. This is a typical thing that you will see in a data center environment that allows the electrical signals to be converted into optical for passage along optical fibers and then converted back to electrical to then be turned back into bits. What you'll see here is that there's a specification that often applies to the whole electro-optical phi, and that is bit error rate. So we need to be able to get a handle on that, and that means typically using simulation with large numbers of bits. So let's move on and take a look at the simulation. Bear in mind, I should have mentioned that you've got different kinds of models here that you need to work with, and that's one of the tricky things. There's circuit level models. There's distributed structures, that's transmission lines. There will be DSP typically in here for equalization, clock and data recovery. And then as well as the electrical, there will also be the optical section, which includes the VCSEL and the fiber and the pin diode and the receiver. So let's have a look at the typical options that we have today. So there's SPICE type simulation. Using perhaps convolutional technology as is found in Keysight ADS. There's some really good things about SPICE. deals well with circuit level. You can do many different kinds of analysis. You get access to waveforms at every node. You can include S-parameter data and EM models. And pretty much everybody working in electronic design is familiar with the SPICE engine. The con side of this is there's really no DSP or easy DSP functionality inside of a SPICE environment. It tends to be slow because of its time sampling nature, which means it has limited DER capability. There's no really a native optical support in most commercial SPICE simulators. And of course, there's the question of proprietary model encryption, which comes up when you need to be providing models to customers and things of that nature. So then we go on. What else do we have? Well, there's system simulators like Keysight System View. What we do here is we build up a different kind of simulation picture. It's still schematic based, but it typically is data flow. And this is good for DSP, for the models and functions, for things like equalization and clock and data recovery. You can do those high-level system measurements if you want to do them. It can be fast, depending on the modeling. A nice thing here is that it can be used to generate C++, and we'll talk about that more in detail later on as one of the vehicles for modeling. Yes, it can work with language. You can deal with electrical and optical because essentially this type of engine really is dealing with numbers rather than particular voltages and currents. And it's very flexible. On the con side, it doesn't do so well with circuit models. There aren't many. They're hard to describe in some cases. It's difficult to include a manufacturing technology. Again, DER capability might be limited because not all of these simulations are fast, so it means that you don't get enough bits to really do DER prediction. And there are many different kinds of system simulators on the market, and I'm sure you're aware of that, and each of them has its own way of doing things. And, of course, if you're a circuit designer like me, you'll see that it's system engineer-centric, and sometimes that can be a challenge. So let's look at a third option here, and that's channel simulation. Now, channel simulation has a lot of good things going for it. We can do waveforms, bit error rate, bathtubs, because it's a very fast simulation technology. And I'm going to discuss it briefly in a second, but yeah, there's plenty of detail in the literature about this kind of engine. You can include DSP functions. You can include EM models, S parameters, and you can also include linear circuit models. And because of this ability to look at DSP as well as a channel, a real channel, you can work with that. You can sweep channels and see if your equalization, for example, can deal with the channel set that you may have to deal with. There is a downside. One is that it requires a specialized modeling technique called IBIS-AMI, and again, I'll just briefly describe that in a moment. And for people who are on the circuit side, there's some unfamiliar, at least at first, DSP concepts. And it's an evolving standard, but that's a good thing as well because it means the standard is in fact evolving. It's not static, and we're continually modifying it. And we'll talk about that as well. Now, given that channel simulation seems to be a good thing for modeling a phi, how does it work? So there are several personalities, typically a statistical personality and a bit-by-bit personality inside of a channel simulator. But I'm going to focus on bit-by-bit here just because that is what we will use with the optical type models. Essentially, this technology allows us to take the step response of a channel. And what we do inside of our tool ADS is that we do a full transient simulation to accurately characterize that step. And that is the core thing here. If that is an accurate process, then the resulting simulation, which uses a superposition of bits, a superposition of those responses, will also be very accurate. And fast, too. There is one assumption that's key to a channel simulator, and that is that the channel itself must be linear time invariant. So we'll talk about that later, but essentially that is how we get speed. Now, we talked about needing to use IBIS-AMI modeling. And again, this is where our VCSEL will fit in a moment. IBIS-AMI is a particular kind of model that's meant to run with a channel simulator. It basically is It's a portable model, and it's got inherent IP protection because the model is actually compiled. So that's a good thing. And the other thing is that this model is also transportable to other simulators that meet the IBIS-AMI standard. So you don't need proprietary encryption keys for modeling to protect your IP, and that's a really good thing. And it means, in effect, you could use one vendor's transmitter and another vendor's receiver, and that's also a very good thing because of the standard environment. Again, it's designed to work with a channel simulator. The performance is important here, and what you can do is you can get very good DER performance. The comment on seconds here is really related to the statistical simulator, but even using bit by bit, you can still get to a billion bits a day kind of performance without too much issue. Let me see. Yes, models can be a linear time invariant or non-linear time variant. That's a good thing. So if you're using, for example, a DFE, that's a non-linear time variant kind of behavior. That can be included here in the IBIS-AMI flow. And it's entirely up to a model vendor what parameters are exposed if you're going to be providing that to one of your customers. Now, having said all that, you say, well, how do I get an IBIS-AMI model? How do I take, for example, that VCSEL that we're going to talk about and put it into IBIS-AMI? Well, at Keysight we have a tool called System View. It's a system simulator, like the one we discussed earlier. And what we are able to do from System View is we're able to generate C code directly, and that C code is then used to build compiled models that go into IBIS-AMI. And the great news with this is that from the perspective of someone who's working with the behavioral blocks, you don't really need to do any coding at all. Essentially, the blocks that we have in our library, and there's more than 130 of them, can be directly compiled into an IBIS-AMI model. And it's a very easy process. Now, to support optical links within that process, we actually have 5 dedicated models that support an optical link type environment. We have a VCSEL driver, the VCSEL itself, which we're going to talk about, multimode fiber and a PIN diode, and a TIA. So those 5 models can actually be used from System View to build IBIS-AMI, a model that you can then go ahead and use in Channel Simulator. Just to sort of show you very, very briefly how this works, once you have a network defined inside of the system simulator that you want to build a model, so that could be, and I'll show you this in a moment, the optical link, then you simply go into a model building interface. You set up some configuration parameters and some model type information, and you press a button that says generate, and then everything else is done in the background for you. So again, no need for C coding on your part. The various model files that are required for IBIS-AMI will all be built automatically. So we talked about optical links for this. How does that work? Well, the original IBIS-AMI standard allowed for a transmitter, a receiver, and a linear time invariant channel. What has happened is the standard was extended at version 6 to include what's called a mid-channel redriver. This is very useful in the electrical-only world because of the need to do repeaters. But the nice thing about this is that you can actually use that same structure to encapsulate an entire optical transceiver, the optical link, if you like, including the fiber, inside of one of these mid-channel items. So once you've worked with System View and you've worked out what your optical link should look like, you can then generate a mid-channel optical module directly from System View and then use it inside of channel simulation. And you can see here that the VCSEL is part of this picture. So let's go along now and start focusing on the VCSEL. Now we've got the context, what we're talking about, where we're going to use it, and what kind of simulator, and study it in a little more detail. So modeling a VCSEL, not a trivial thing to do. It has, characteristics that we're all pretty much aware of. It's short haul for the most part. Can support high data rate. So the model has to be able to deal with that. We're working with low powers, typically milliamps, milliwatts. We need to be able to describe the electrical to optical transfer characteristic correctly. And one thing about VCSELs, as anyone who's worked with them will know, is that they have a critical thermal behavior, and any modeling that we do has to definitely include that. And the application, data transmission in the data center, any modeling that we do typically would need to be useful in that context, the ability to do simulation. So what options do we have for VCSEL modeling? So let's look at a few here. Well, first is we could use a 3D modeling and simulation environment, which is a great and accurate way to do things. But that kind of modeling tends to be complex and, as such, fairly slow, and so really isn't suitable for working in electrical or data flow type simulation. So what other options do we have? Well, we could create a SPICE type model, and one option would be to use physics-based rate equations, and that's good. You end up with a fair simulation speed because it's in SPICE, but again, there may be concerns here about IP issues for model sharing and those kinds of things. Then there's the IBIS-AMI approach for use of channel simulation. We're really here trying to get a behavior. What we do is we can build a model that treats the VCSEL as an algorithmic unit, that is a block inside of a system context. Again, we can use those physics-based rate equations. And the nice thing is, because we can do that and build it into an IBIS-AMI model, we can use it in a channel simulator, which is very fast. It allows us the ability to do lots of bits and or lots of different simulations, swept simulations, so that we can examine the design space. We can try different things. And with the challenges, we're facing with these different, things like high-order modulation that we talked about earlier, that the ability to do many simulations is a good thing. And of course, the nice thing, as I mentioned earlier, is that there is inherent IP protection in IBIS-AMI. So let's focus on these rate equation type models. Why are we looking at those particularly? Well, the nice thing about the rate equation type model is that it can be constructed to capture temperature dependencies, and it will model the appropriate relationship between the input current and the output optical power with that temperature. And because of its nature, it's actually quite suitable for working with electrical and data flow simulation. It has a good compromise between speed, complexity, and accuracy that makes it very useful. So the model that we've chosen to implement is from the paper here reference. I'm going to call it the MMKHW model, in order that we're not here until after our time. And that's the one that we chose to put into Keysight System View, and therefore, because it's in System View, we can then build it into an IBIS-AMI model. As previously described, it's rate equation based, and the equations are such that there is also the ability to deal with thermal issues through the inclusion of a thermal offset current. And it's suitable for time domain, bit-by-bit type analysis, data flow analysis, and also for stationary analysis for things like LID curves. You'll see here at the bottom of the slide the paper is fully referenced, along with a second paper that was done at DesignCon in 2014, which also contains some really good information on this model. Now, the thing is, once you've chosen a model like that and you've implemented it, you still have to be able to fit the parameters for those equations that we saw. We have to be able to feed in the right numbers in order to get the right behavior. And that right there is a seriously challenging thing. The good news is that as part of our optical setup inside of System View, we have produced a VCSEL extractor module, which you can put into a simulation, as you see here. Not a very complicated thing at all, very simple in concept when you get down to it, which allows us to take in measured data, and from that measured data, extract the appropriate parameters in an automated way. So what we do is we take VI curves and LI curves typically, and also, if we have it, the frequency response curves, and use that information and some curve fitting algorithms to produce a set of coefficients that can then be used by the target VCSEL. And interestingly enough, if you had implemented this model in a SPICE environment using the same kinds of equations, this data would be equally applicable there. This is not a special set of data. It really does apply to this rate equation model, which could also be used in a SPICE environment if you have the same model there. So what do the measured curves consist of? There's the LI curve showing the relationship between the input current and the output power, optical power, and also at different ambient temperatures, and that's important for us to get the temperature dependence as part of the characteristic. Then there's the voltage current characteristic, also as a function of temperature, and then the H of omega frequency type response, which will also give you some idea about the bandwidth capabilities of the model. So how do we do the magic? How do we take that into data and turn it into a set of parameters we can use? Well, again, I'm just going to give you a highlight here and say that we use two different kinds of curve fitting. One for the simpler equations where we can do direct extraction, and then the other one which requires an iterative type approach for the more complex relationships. The paper that you see referenced here at the bottom goes into that in good detail, and I would certainly recommend, if you want to see how this is done in detail, that you reference that paper. So what does that look like? So here is a set of modeled and measured curves overlaid on top of each other, and you can see that the resulting extraction is actually very close to the input measured data at the temperatures given. So that's a good checkpoint to say that looks like it works. The same is true here. This is a VI curve fitting result. Again, very close between the original measured slopes and the predicted simulation. So you've done this extraction, so what do? The next thing you want to do is you want to do some verification. So we have some, like a test harness, if you like, that allows us to then take the VCSEL model, not the extractor, but the VCSEL itself, using a file, point the VCSEL model at the coefficients we extracted, and then run some tests. In this case, you're seeing a system which on the left side is inputting a sinusoidal waveform with a given frequency, together with a biased current, and then that's summed together. And then the VCSEL model itself, and you can see that the blocks that show 1, 2, 3, those are data sinks where we capture our data. And then we're doing a very simple block, actually like a MATLAB block here inside of System View, because System View supports the ability to use MATLAB code. And then calculate the frequency response, which is the bottom right-hand sink, the 1, 2, 3 in the bottom right-hand corner. So that's giving us a frequency response. So we can use this setup to sweep both time and frequency. So what do the results look like? So here we're looking at, is the behavior reasonable? So the input signal is the blue line, and that's you'll see that it's scaled in milliamps on the right-hand side if it's not too clear. And then optical power is in green. And this shows the startup from the very beginning of the simulation to where you reach a steady state. And you can see that after settling down, the optical signal is responding correctly to the input electrical signal. And here is a swept frequency model. Here we're looking at the frequency response on the lower axis versus we'll call it, it's like an S21, but it's for optical power. So in other words, we're looking here at electrical energy into optical power add. And you can see here that there's a definite peak, but that the response is actually good to probably in the region of 10 to 12 gigahertz. That's for small signals. So can we do large signal testing? So a waveform test. So this is another test harness that does pretty much the same thing. we create a two-level signal. I won't go into the details here, really not the time or place, but it's very simply done. We add a bias current to it, and then we modulate the binary, the NRZ waveform onto that bias level into the VCSEL, and then we take the data out, and then we look at that. So here you'll see a trace here. The blue is the modulating current. It's swinging between 4 and 20 milliamps. And the green is the optical power being measured coming out of the VCSEL model. So in terms of behaviors, we're getting behaviors that we like and look good. So let's look at some data here for comparing a couple of device cases. So on the top side here, you'll see that there's Li and Vi curves for this particular model. This is pretty much the same curves that you saw earlier. And again, you see a very good match between the input measured data and the extracted performance. And then at the bottom, the simulation, we see the Li curve here under different simulated temperatures other than the measured data, and also the time response I showed you earlier. Let's move on to a different device. So here we have Li and Vi curves, and also a frequency response curve on figure 3. And then on the lower side, you can see some simulations for, again, Li data at different temperatures, the frequency response, and also large signal response. And the last case I'll show is where you could actually do this verification in the context of a full system. So this is running inside a system view. You'll see the basic blocks here of a full optical link from the VCSEL driver through to the TIA. And we can look at the electrical performance of the output, and you see the waveform there in the eye diagram generated from system view. And at the bottom, there is a screen capture of the output from our FlexDCA software, and that is simply achieved by placing inside of the system view sink, inside of the system view schematic, a sink, if you like, which represents the FlexDCA software. And when the simulator runs, it launches FlexDCA, and it behaves just like it would if you were doing real measurements on the bench. Which, of course, facilitates some very simple comparisons between simulated data and measured data, because you're not having to worry about, is the measurement environment the same? Am I using the same algorithms? You absolutely are. So let's look at this in a. We've seen the model. We've included it in IBIS-AMI. We've done some testing. We like it. We ran a system simulation, the last one, and we built ourselves something we like as a model. So let's turn that into an IBIS-AMI and use it inside of a channel simulator and see what we can do here. So this, I apologize for these next few slides. They're a bit of an eye chart. Hopefully you'll be able to get this material later on and see this a little more clearly. But this is a setup inside of Keysight's ADS where we're looking at 4 25 gigabit channels in a transceiver. The transmitters are on the left side, and the receivers are on the right side, even though they're a little bit covered by some of the graphic. And the optical link is embedded between 2 electrical link simulations, and it's the center triangle, if you like. It says optical links at the top. And what we have here is a victim channel and 3 aggressors, effectively, and that's the analysis that's set up here. But the key point here is, remember we talked about VCSELs having thermal behavior? Well, what we're doing here is we're enabling ourselves to look at a link with all of the crosstalk, electrical and optical, all running together, and sweeping the ambient temperature of the VCSEL and seeing what is going to happen. So ambient temperature is one of the parameters that we allowed to be built into the IBIS-AMI model, and then we can assign that a variable inside the ADS and sweep it with a batch simulation, and we run a channel simulator. So what do the results look like for that? So here's just a couple of screen captures. That it's there's a lot more detail that could be shown if you were looking at the example. And hopefully, if you would like to see the example in detail, then please contact us. But you'll see here I just captured two eye diagrams at the output of the whole system. One at a temperature of 30 Celsius, the other one at 50 Celsius. And you can see how much the eye has started to collapse. And if you were to push this even further, you would see that by the time you get to 70 Celsius, the eye is pretty much completely closed. The dotted lines in the middle are actually error rate contours, if that was of interest. And you can see also on the right side here the swept bathtub. So this is like a nest of bathtubs at different temperatures that were run during the sweep. So you can see that after a certain temperature, the bathtub basically is closed, and you simply aren't going to get any good performance from this particular item. Now, one of the other issues that can come up in discussion is, well, you have your optical link. Can I break into that link? Can I do anything in the link? One thing that you might want to model, for example, is the coupling inside of the VCSEL array. The VCSEL, in a sense like this, will probably be a number of VCSELs all on one piece of semiconductor. And guess what? When you're feeding them, there's an amount of crosstalk that's not modeled in the input and output channels of the package. It's actually right there at the die. Well, what I've done here is I've split the optical link into two. I put the VCSEL driver as one stage, and the rest of the optical link from the VCSEL onwards as another. And you can see that I put a block in the middle, which is I'm using, it's a fairly simple model inside. It's looking very, very complicated, just cross-connected capacitance, very low-level capacitance. And I'm allowing the crosstalk to occur between the VCSEL driver and the VCSEL itself. So again, it's in the electrical domain. That's an interesting level of fidelity that you can get to. So we're looking at two things here. One is we can model things that you might not readily think are doable. But yes, you can break up a given optical link into multiple redrivers and use them cascaded, as I've shown here. So let's look at this in brief. Actually, it's a very simple swept analysis. I did just two steps, one with the coupling on, one with it off. And you can see, if you look closely at the eye, that the VCSEL, when the VCSEL coupling is turned on, the eye is more closed. And also you'll see that some of this little bit of empty space in the lower part of the plot that's now closed over as well. And there's a number of extra closure all around the plot. So definitely signal is breaking through due to this coupling. And if you look at the comparative bathtubs on the right-hand side, you can see that they are showing considerably more closed. I mean, this is a very simple model, and you would need to fit this model to your own needs. And we'll look at one last one here. This is where someone was looking to see if we could do PAM4. And I put this together, and what we're going to do here is on the left-hand side, instead of an NRZ type transmitter, we actually have a PAM4 transmitter, and we're going to feed it through the same optical link. This optical link was designed for NRZ signaling. So, is it going to work? What's it going to look like? It's an interesting question to take an existing design and see whether we can use a higher order modulation. So on this diagram here, you'll see on the top left is the transmit waveform, the PAM4 input. And then you'll also see the PAM4 as designed. So this was 16 milliamps. The NRZ signal looked actually pretty good, but the PAM4 signal looks terrible, and you can see that we're definitely a long way up the LI curve here, and there's a lot of nonlinearity occurring at the top end that was not apparent at all in the NRZ signal. But clearly here, where we're trying to look at discrete levels, it's certainly important. So one of the characteristics of that previous schematic was I was allowing myself to sweep the bias current into the VCSEL. So again, I showed you swept temperature, and I'm sweeping the bias to see if I move the bias point, can I get the eyes to be any more open? And the answer was I could to a point, and that's what you see at the bottom. When I changed the bias current to 12 milliamps, you'll see that the situation was improved, but it's still not wonderful, and it doesn't, in fact, take a great deal of work to make a VCSEL type work in multi-level high-order modulation. But it's an interesting that you can actually run a test like that at a system level and see the whole performance of the phi. So that's it for the presentation. I'll just run to the conclusion here. Faster data rates, new technologies like the PAM4 I just showed make full Electro Optical Link simulation at the phi level highly desirable, so that you can see as things are changing, as you're being challenged over data rates and modulation formats, what's going on in your system. Channel simulation provides a great vehicle for doing that because it's fast and it can use the IBIS-AMI model, which we've shown we build optical links. Accurate modeling of the VCSEL is perhaps one of the most critical parts of the optical link, and you need a temperature-dependent model for that. The rate equation-based model in the paper that we have implemented, along with our extractor, which takes the burden off of you for developing the correct extracted parameters, really enables you to work with the VCSEL and measure data and get good answers. And you saw from some of the simulations I showed that the extracted model shows good agreement with the measured data, so verifying what we were doing. And then lastly, I showed you some examples of a full channel simulation of different parts using optical link, and you were able to see how we were able to work with the detail. So that's it for the presentation. Let's move us along to the question and answer session.
Great. Before we begin the question and answer session, we would like you first to help us improve our webcast and answer a couple short questions about what you saw today in the slide window. Please select the answers that you feel best. Question 1, please rate your overall satisfaction with this webcast. Question 2, based on what you heard today, would any of the below products have value in your work? Finally, do you have a time frame when you plan to purchase a solution? And finally, don't forget to check out the exit survey. Thank you for your responses. Now, on to our question and answer session. And for the first one, can you address other types of optical links with this flow?
Yes. So it's always good to be able to answer a question and say yes. Yes, you can. I'll put a small caveat on that and say it does depend upon having the appropriate models for the elements of your link. We provide a certain set. You saw those, the 5 models. If you can work with those, you can pretty much do what you need to do. If you have other needs, for example, a monomode type arrangement or a DFB type laser, the answer is still yes, but you would need to do some work providing the models. It's possible that our VCSEL model could be used. It's rate equation based for something like a DFB. Has the same underlying laser equations. So Yes, I'm going to say yes. We could use this in principle for other types of links, even potentially for things that use quadrature type modulation.
Okay. Next question is, what format would be needed for the measured LI and IV data?
So that's actually pretty easy to address. It's a simple text file. Essentially, it's sets of Li pairs or Vi pairs as a function of temperature. It's a very simple text file format, and we'd certainly share that with you. And typically, some form of simple scripting can be used to turn pretty much any system data into the right format to be used by the extractor.
Okay. Your simulations show a single EOE in the channel path. Is it possible to have more than one repeater redriver in the signal path?
Yes, it is. The way our channel simulator is set up, it means you can have multiple repeaters. In fact, I did show that when I showed the VCSEL cross-coupling, VCSEL array cross-coupling. That really was a breaking the optical link into two redrivers, and that approach could be extended. Like anything, if you have more, the simulator will take longer to run, but certainly in principle, both in terms of number of parallel paths and number of sequential redrivers, there's no limitation.
Okay. Does the temperature model include self-heating, where the temperature increases with the long strip of ones?
Can you repeat the last part of the question, please, Bill?
Evidently, they're talking about if you send a long series of ones through as data.
I see. Okay. So I think the way the model is formulated, it means if we're making an assumption about the thermal time constant here, from what I remember in the model. Again, I'd have to look back at the paper, but there is kind of an assumption that if the sequences of ones and zeros are less than the typical thermal time constant of the model itself, of the device itself, really, not the model, but the thermal time constant. I hope that answers the question. If more details, but
yeah, I think so. And we have one more question here. Something shown in system view, not the VCSEL generation, could be done with ADS with Ptolemy. Why is that not told? That's an interesting one.
So why are we using system view and not Ptolemy? Is that the question? Is that really what it boils down to?
That's what it looks like. ADS Ptolemy.
Yeah. So system view is a dedicated tool for system level design. As I described earlier, it's typically data flow based. It allows us to do DSP functions and those kinds of things. And the questioner clearly is familiar that there's an engine inside of ADS called Ptolemy, which can do similar things. The reason the Ptolemy setup inside of ADS is really there as a validation type environment. It's not there for system level development work per se. System view is a much easier tool to do IP development in. In other words, inside of ADS, you might think about a reference system. Inside of system view, you create that system. You can generate models just like we generate IBIS-AMI. The whole environment is set up really to do that. So I hope that gives a sufficient answer, but that's really the context. One is for IP creation. One is for really validation of circuit level work. Okay.
Well, that concludes today's presentation. You're also invited to register for our next webcast, How to Use SerDes Channel Simulator for PAM4 Simulations and Analysis, on July 23rd. On behalf of Electronic Design, I'd like to thank you for joining today's webcast. And we would like to thank Keysight Technologies for sponsoring this event today for us. Have a productive remainder of the day.